Okay, the topic for today's lecture is sustainable development and human populations. We're going to talk about humans and population ecology, learn about population consumption, growth, and affluence, and learn how to apply an equation to project population growth. We'll also talk about demographic transitions. And then finally, we'll talk about sustainable development and social modernization. So humans, as you know, we're part of the natural world. We're subject to processes like births and deaths, just like many other animals. And so the population growth curve for the human population historically has displayed what we call a J-shaped curve. So for quite a period of time, as you can see in the figure on this slide, there was very little growth in the human population. You could see some dips, like for example, during the Black Death Plague, but then the population rebounded, but there really wasn't any substantial growth until we get into the 1800s, 1830, around that time. That's when you start to see the population growth increase almost exponentially, reaching to a total population of approximately 7.5 billion, which is where we're at today. However, it's projected that by the year 2100, the growth in the human population will likely start to taper off, displaying more of an S-shaped or logistic type curve, right, as we reach the carrying capacity of the Earth. So in biology, there are what's referred to as R-selected species versus K-selected species. So R-selected species tend to be animals that have a high reproductive potential. They tend to have shorter lifespans, younger age of reproduction, and their population can grow very rapidly. A K-selected species would be animals that remain closer to their carrying capacity. They're characterized usually by longer lifespans, having an older age at first reproduction, and relying on parental care. So an example of an R-selected species would be like rabbits. An example of a K-selected species would be something more like elephants, for example. Humans, it's important to note that we're critically different from other species in many different ways. So with respect to growth patterns, we display characteristics of R-selected species like exponential growth potential, but we also rely on high parental care, and we have a late age of first reproduction, which is more consistent with K-selected species. Right, and so you see that with the trends in the population growth for the human population throughout the years. And certain revolutions have drastically changed our lives and also influenced the growth patterns that we've experienced in population over the years. So for example, during the Paleolithic period, 50,000 to 10,000 years ago, humans lived in small tribes, mostly as hunters and gatherers, and they were constantly moving. There was very common for these humans to experience death from predators, death from disease, and also famine. However, the Neolithic Revolution sort of changed all that, right? So before agriculture, humans had to forage for food, but agriculture allowed people to settle into cities and to divide up labor to, allow humans to settle and form larger populations. The Industrial Revolution is characterized by introductions of the use of coal and other fossil fuels to power machinery. And here's where you see the start to a lot of engineering solutions to create economic growth. However, at the same time, they created an increase in pollution. The medical revolution also greatly contributed to the large growth pattern that was experienced in the human population in the 1800s and 1900s. So before the 1800s, there were many diseases like smallpox, measles, that were caused by infectious agents like bacteria, viruses, parasites, and they would greatly affect infants and children in particular, causing, in some cases epidemics like the Black Plague, which also would affect adults. And this would control the population in humans to a certain respect. So there were high reproductive rates during this period, but they were balanced at the same time by higher mortality rates, resulting in an overall low population growth rate. So in the late 1800s, we experienced spectacular decreases in child and infant mortality, in particular due to the invention of vaccinations, the treatment of sewage and drinking water, penicillin, and other antibiotics as well, improvements in nutrition. And so you start to see higher birth rates with decreasing mortality rates. That really helped influence this exponential population growth pattern that was experienced. And a lot of these were engineering interventions as well, like the treatment of sewage and drinking water and medical field, engineering influences into the medical field that allowed for this type of population growth. The agricultural revolution, or the green revolution, also influenced human population patterns. So the population growth that was experienced caused a demand for higher yields from agricultural crops. So the use of fertilizers, irrigation, pesticides, and the introduction of new crop varieties was developed. So this industrialized type of agriculture helped feed the growing population, but also came at significant costs. So soil and water are used faster today than they can be replaced, and problems like erosion, soil and water pollution, the loss of native species, and the resistance of crops to pesticides has increased, creating new types of environmental problems. So take a moment and think about this. When humans began to move from this small, sustainable populations to larger populations with the help of modern medicine and engineering interventions, how was this growth handled? What were some of the environmental consequences? And I want you to think in particular about land ownership, the cultivation of crops, land use changes, migration patterns, and even more importantly, the purpose of local governments. Why we have governments today. What is their purpose? Okay, it's important to note that different populations have different levels of environmental impact. And there's a popular model out there called the IPAT model, which basically suggests that the environmental impact, I, is a function of the population, P, the affluence of the population, A, and the level of technology used in the society, T. Right, so what's the effect of population? All right, this one is pretty straightforward. Since the Industrial Revolution and other revolutions, like was explained earlier, the world's population has drastically increased, causing an increased stress on the world's natural resources like water, soil for growing crops, etc. Two, the effect of affluence. So increasing the wealth and affluence of a population often results in the increased consumption of goods, services, and amenities. As we experience higher quality of life, we're also consuming more resources. This generally increases environmental impact. A proxy measure that's used for the effect of affluence is usually GDP, or gross domestic product, per person. Now, it's important to note that there are some potential for increasing affluence to result in some decreases in environmental impact, but in general, it's more common that increasing affluence will increase also the environmental impact. Three is the effect of technology. So with increasing affluence, sometimes can also come increasing innovation and development of new technologies that can even decrease the environmental impact of consumption. So some technologies, as you saw with the Industrial Revolution, increased affluence, but drastically increased environmental impact as well. Currently, modern technologies that are designed to maintain the level of affluence and the level of exposure to goods, services, and amenities, but also decreasing the environmental impact. More sustainable technologies is an effect that technology can have on actually reducing the amount of emissions per unit of consumption, right? So a proxy measure here is usually the amount of emissions per unit of gross domestic product. All right, so there are great disparities throughout the world in terms of the amount of access to resources and affluence, right? So we can show the breakdown of different countries in the world in terms of whether their economies are characterized as low-income economies. That would be, mostly countries you can see here in sub-Saharan Africa, some countries in the Middle East and South Asia, countries that are considered middle-income economies, seen in Asia, the Middle East, Eastern Europe, parts of Africa, as well as Latin America. And then high-income economies, which you can see are characterized here as regions in Australia, New Zealand, Singapore, most of Europe, especially Western Europe, Russia, the United States, Canada, etc. So if we look at the amount of people in different regions in the world and kind of magnify that by the poverty index of the different regions, we can see that the regions where the most people living in poverty are shown here in the map, right? You can see India, many countries in sub-Saharan Africa showing up as very prominent in this map, as they have larger populations and also high human poverty index, right? So human poverty has a lot to do with affluence, environmental impact, and also population growth, which we'll talk about in a minute, right? So there's a trend that's seen in world populations in terms of the total fertility rate, which influences the population growth rate, and the per capita income of a country. So you can see on this graph on the lower left that countries which have a low per capita income, so a higher poverty index, also tend to have higher total fertility rates. As you can see, the Democratic Republic of Congo, Uganda, Mozambique, Sudan, Madagascar, all having per capita incomes of less than 3,000 and total fertility rates above 4. Whereas countries that have higher per capita income, like Kazakhstan, Malaysia, Panama, Turkey, Chile, are shown here on the graph towards the right side. You can see they also have fertility rates less than 3. So this has been described as the poverty demographic cycle. Right? So societies that live in poverty tend to overuse resources for survival. So this leads to environmental degradation. In return, those families need to have more little hands or more children in the family in order to help grow food, help subsistence agriculture, and to survive in this depleted environment. This leads to a high fertility rate, which consequently causes dwindling resources to be divided amongst more people, which leads to more poverty. So it's kind of like a cycle that's experienced in the context of food insecurity, a lack of employment opportunities, and a high disease burden. We see shifts in health patterns with development and with increases in affluence. So developed nations or high income nations and developing nations or low income nations tend to have very different causes of mortality. In general, the least developed countries, lower income nations, tend to have the highest impact on health coming from communicable diseases like infections caused by lack of water and sanitation, lack of hygiene. Whereas in developed countries and higher income countries, you don't really see communicable diseases as causing such a significant health burden. However, cardiovascular diseases, cancers start to become more prominent as people live longer and are more susceptible to different types of illnesses. And as mentioned before, there's a very big difference in the population growth rates in developing countries versus developed countries. So in developed countries, as you can see from the data here, from the year 1950 up till today, with projected population growth up till the year 2050, you can see for developed countries, it's pretty much steady. There's not too much growth, there's not too much decline. It's projected that they'll maintain a relatively steady population at around 1 billion. Whereas developing countries, the lower income populations of the world, their population has increased from 2.5 billion in 1950 to currently around 6 billion and is projected to continue increasing at a higher rate than developed nations. So as mentioned, the consequence of affluence, there's the high consumption of affluent populations places enormous demands on the environment. The world's wealthiest 20% of the population is responsible for 86% of all private consumption and 80% of all world trade. So high inequities in terms of access to goods and resources. Environmental problems in many affluent communities, rather than being eliminated, are just pushed into other places. So unfortunately, rich nations tend to import resources from poorer nations where pollution laws are not as well enforced. And this basically just shifts that environmental impact from the wealthier nations onto the poorer nations. And it's well known that affluent communities have higher rates of waste generation. So when this shifts, when these environmental problems are just shifted or pushed into lower income nations, it's not really solving the problem, it's just shifting it and increasing the inequities between those nations. So a popular topic today in terms of technology development is the application of advanced technologies to reduce environmental impact, right? And so you see here from the image, the Tesla being an example of one proposed solution to the problem of environmental pollution from vehicle traffic in wealthier nations by creating one of the first entirely electric vehicles. However, something like the Tesla may solve the problem of local emissions due to pollution caused by vehicle exhaust. However, there still are emissions associated with production and the use of vehicles like the Tesla cars. Right, so the production of those vehicles, the factories used to build the parts, to extract the resources like the metals and the materials used in the batteries, all of that has an environmental impact. It's really just that the impact is now more focused on the factory and the production cycle than the use cycle of the vehicle. And that's just one example. There are many other examples of technologies that can help reduce environmental impact. However, as we develop and design these technologies, we also need to be conscious of the life cycle impact, meaning the impact resulting from the production of the technologies themselves. When we talk about sustainability, we really need to think holistically in terms of the life cycle of products, the life cycle of engineering interventions, and reducing the overall life cycle impact, not just the impact during the use stage. Okay, so getting back to population growth, of course, we've got great differences in the projected population growths of more affluent nations versus less affluent nations. In terms of the overall world population, which is currently at about a little over 7.5 billion, the projected population under different growth scenarios can be seen here in this graph, which comes from your reading for this module. So we can represent some of these growth patterns mathematically, and we can use an equation to project future population growth for the purposes of engineering design, right? So we can make assumptions about whether the growth is high, medium, low, whether fertility rates are maintained constant or whether they start to decrease in the future. A simplified growth model is shown here, where you can see the future population, P sub F, can be represented as being equal to the current population, P sub P, multiplied by 1 plus R, which is the population growth rate, raised to the n power, where n is the number of years into the future that we're projecting population growth. And so just like the previous figure, showing high growth rates, medium growth rates, low growth rates, you can see here in this figure, if we were to assume a future world population growth of 1.6%, then we would have the pattern here shown in blue. And by the year 2100, we would have more than 25 billion people in the world. However, if the growth rate stays below 1%, like 0.8% growth, the population at 2100 would be approximately 15 billion people. And if we have a lower growth rate, like 0.4%, we would have slightly more than 10 billion people by the year 2100. All right, so how can we apply this equation? Let's look at it in a little bit more detail, right? So what we're calculating here is the future population growth, P sub F. And in order to estimate that future population, how many people will there be in the year 2100, let's say, we need to know what the current population is, and we need to know how many years in the future we're projecting that population out. So if it's projecting the population in the year 2100 and it's currently 2021, then that would be 79 years. So n would be equal to 79. Or, you know, if the year was 2020 and we were projecting out to the year 2050, that would be n equals 30 years, 2050 minus 2020, 30 years into the future. All right, R is the growth rate. So this is how much the population will grow each year. And the current population growth rate in the world tends to range between 1.5%, sometimes less than 1%, depending on the region. So you can see if we know how many years in the future we want to estimate population, and we know what the projected growth rate is, and we know what the current population is, then we can calculate the future population. At the same time, we can also calculate the growth rate if we know what the population was in 2 different years, and we calculate the difference between those years. So for example, if we had historical population, let's say in the year 1950, and we're comparing that with a current population of the year 2020, let's say, that's a difference of 70 years. So P sub F could equal 2020, the current year. P sub P could equal 1950, the past year, and N would equal the difference between those 2 years. Right, so 1950 being P sub P, 2020, if we take 2020 minus 1950, that would be 70 years, so N would equal 70 years. And we could rearrange this equation algebraically and solve for R to find what the growth rate was during that period of time from 1950 up to 2020. All right, so we can use this equation in a number of different ways. Let's see an example problem. So we're going to take the example of the state of Utah, which has one of the highest population growth rates in the United States as of the most recent census. All right, so if the population in Utah was 2,763,885 in the year 2010, let's use the equation we just saw to calculate the growth rate R between these 2 years. That'll be part A of this example problem. For part B, we will assume an annual population growth rate R of 1.4%, and we'll use the model to estimate the future population in the year 2030. All right, so this is a 2-part example problem. We're going to start with part A. So for part A, the first thing we want to do is plug the values that we know into the equation and then solve for R. So remember, in this part of the example problem, we have the historical population in the year 2010. We have the current population in the year 2020. So that's a difference of 10 years. So n is equal to 10. And we want to calculate the growth rate, R, between those 10 years. Right, so we put the current population in for P sub f on the left-hand side of the equation, 3.2 million. And we put the past year's population in the equation here for P sub p, 2.763 million. R is unknown. So then we just rearrange this equation algebraically to solve for R. So the first step is we divide both sides by 2.7 million. Right, that gives us on the left-hand side of the equation, 3.2 million divided by 2.7 million is equal to 1.176, and that is equal to 1 plus R raised to the 10th. Then, in order to further rearrange this equation to solve for R, we take the natural log of both sides of the equation. All right, so the natural log of 1.176 and the natural log of 1 plus R raised to the 10. And when you take the natural log of 1 plus R raised to the 10 can be brought in front and made into a multiplication. So we have 10 times the natural log of 1 plus R. All right, so that's an algebraic simplification of 1 plus R raised to the 10th. If we take the natural log, it becomes 10 times the natural log of 1 plus R. Okay, so that leaves us with the following equation, and we're still trying to solve for R. We can divide both sides by 10, and then we can take the exponential of both sides, so e raised to whatever we have on both sides, in order to solve for R. That gives us the final form of R being equal to exponential, the natural log of 1.176 divided by 10, and that whole thing minus 1, which equals 0.0163. So in order to express that as a percentage, we multiply it by 100 and we put the percent symbol behind it. Right, so the growth rate between 2010 and 2020 in the state of Utah was 1.63%. All right, so that's part A of our example problem. For part B of the example problem, we're going to plug in the values into the equation and calculate P sub f directly. So as a reminder, in part B of this example, we're now going to project the future population growth rate. So historically, in the past 10 years, the growth rate we calculated was 1.6% approximately. However, for the future population growth rate, we're going to assume it's a little bit lower. We're going to assume it's 1.4%. And we're going to use the growth rate model to estimate the population of Utah in the year 2030. All right, so in this case, P sub f equals P sub p times 1 plus R raised to the n. N is still equal to 10 because however, in this case, it's 2030 minus 2020, because we're going to use the current population and we're going to project out to 2030. So that's difference is n equals 10 years. And R, we know, or we're going to assume, is going to be equal to 1.4%. So in order to use it in this equation, we have to divide 1.4 by 100 to get it back into a fraction. That gives us 0.014. And then P sub p is the present population, which is 3.249 million. Right, 3,249,879. All right, so the only thing we have left to do is calculate this value here, which will be equal to P sub f, which is the future population in the year 2030. And if we complete that calculation, we'll find that this is equal to 3,734,623, which would be the projected population of Utah in the year 2030, assuming a growth rate of 1.4%. So as populations grow, the breakdown of the different demographics in the population can also change. And as growth rates change, the population profile, what we call the population profile, will start to look a little bit different. So the population profile refers to the breakdown of the number of people in a region, like let's say the United States, in different age groups, right? So you can see here, males shown on the left, females shown on the right, and we have the breakdown of the population by age group. So 0 to 5 years old being shown right here, 5 to 10 years old being shown right here, 10 to 15 years old, 15 to 20. So now we can see the breakdown of different age groups and which age groups are the most populous in the population, right? So in the 1980s, in 1985 in the United States, the age group with the highest population was in individuals who were in their 20s and their early 30s. And this is that baby boomer generation as they were coming of age into their adulthood. Now, as we see the growth pattern change, this is in the year 2014. Now, of course, in 1985, people who were in their 20s, by the year 2014, that is 30 years later, right? They're going to be in their 50s and maybe 60s, right? So you see this, this kind of bulge in the population profile moves up to the 50s and 60s category by 2014. And at the same time, you see still a high growth of individuals in the age groups in their 20s and 30s, and those would be, in general, the children of that baby boomer generation. Right, but you also see the population growth rate start to decrease a bit, and you see the flattening of this population profile, right? So now we have pretty consistent number of people, children, teenagers, early 20s, 30s, 40s, up to 50s and 60s, with a decline after that as you start to get more people dying. As people start to live longer, this population profile will increase and become fatter even up into the larger age groups. So that's another effect that you're seeing here, is the effect of people living longer due to increases in health and medicine. So let's take a look at some other examples. Here's the population of Sweden in the 1950s, right? We've got a large bulge of individuals in their 30s and 40s. We've got very few individuals in their teens and 20s. And then we've got a larger number of children below 10 years old. By 2010, this population growth had sort of equaled out, but the shape, changes a little bit, generally because you have people living older. The average lifespan was probably a lot lower in the 1950s than it was by the year 2010. All right, so you see people living up into their 60s and 70s more commonly. The projected population profile in Sweden in 2050 is pretty similar to what it looks like in 2010. A little bit thicker in the older age groups, so projected that people will live longer, even into their 70s, 80s would be more common. But you still see a pretty flat profile when it comes to the different age groups due to the projected population growth rates. All right, and here's 2100, even more flattening out projected, right? So let's contrast that to some countries with very different population profiles. And this is from your textbook, from your assigned reading. This is Burkina Faso and Indonesia in 1950. You see a very triangular growth or age group pattern, demographics pattern, where you have very low life expectancy in both countries, very few people surviving into the 70s, 80s, and 90s. And you have a relatively larger population of younger people. And that's characterized by people having larger families. All right, as we see the change from 1950 to 2010, you can see the differences in Indonesia versus Burkina Faso. So Burkina Faso still looks very much triangular, characterized by larger families, so larger larger ratio of children to adults, lower life expectancy, and a high population growth rate, with also a higher death rate. In Indonesia, on the other hand, you start to see the flattening out of this demographic profile. So you start to see a slightly lower population growth rate, however, still a large number of young people and a fairly high death rate, especially compared to the earlier example we saw with Sweden, which has a much larger proportion of people living into their 90s and 100s. All right, and the projected growth rate in Indonesia is projected to decline, which will result in kind of a slimming down of the younger population and a larger percentage of individuals living into their 40s, 50s, 60s, and 70s with a lower death rate. Whereas the projected population in Burkina Faso by 2050 is still pretty much triangular. So families are large, there's a high proportion of children to adults. The death rate comparatively is most likely projected to be higher in Burkina Faso than it is in Indonesia. So Indonesia is a country that has experienced rapid development between the 1950s and the 2000s, right? Whereas Burkina Faso is a much lower income country that still has very high growth rates and high death rates. All right, so think about this. Consider the situation of the population in countries like Italy or Japan, and these were described in your reading assignment. So these countries are both characterized by higher incomes, but lower birth rates and in general aging populations. Contrast that to the population situation in countries like Sweden, Indonesia, and Burkina Faso. So refer to your book when answering this question. Think about, what policies might be recommended in these countries if the desire is to achieve a more sustainable society. How could people in these countries help others in order to be stewards of their resources better or to promote a more sustainable future? All right, so again, the population growth rate varies from country to country, from region to region, and even within a country from state to state. And it also, it's influenced obviously by the total fertility rate, which correlates to a great extent with affluence, as you can see here, with total fertility rates being much higher in sub-Saharan Africa and South Asia. Although in South Asia, where you see more rapid development in some regions, you see fertility rates decreasing. And you see generally low fertility rates in places like Europe, which has higher affluence, and also in places like Japan and also the United States. So as countries and regions increase their economic development over time, the fluctuations in the birth rates and the death rates result in these different phases in population demographic transitions, which are described here in the graph, right? So let's take the example of countries that we would classify as being in phase one, that have a high birth rate, a fluctuating death rate. Some examples of countries that fall into this category are Afghanistan, Uganda, Zambia. So there's relative stability in the population demographics. We also saw this as in the example with Burkina Faso. Right? You have a high birth rate, relatively high death rate, which may fluctuate, but it stays relatively high compared to other nations. All right, when birth rate is relatively equal to the death rate, the population profile stays pretty consistent. It doesn't change too much. Phase two is characterized by countries that experience declining birth rates and also declining death rates. So some examples of countries that fall into this category are Ghana, Guatemala, and Iraq. So here you see the birth rates start to decline, as you get into a fertility transition from high birth rates to low birth rates. And as the death rate declines due to better healthcare, better overall health of the population, you see this epidemiologic transition, which comes much faster than the birth rate transition, the fertility transition, because again, it takes a long time for humans to get to their age of fertility, 20s, 30s, where they start having kids. Whereas the epidemiologic transition, the death rate, will decline much faster with increases in healthcare. So during this period, you get a much larger overall rate of population growth. So when the birth rate is still high, but the death rate is very low, the population grows very rapidly. Now, in phase 3, the birth rate declining based on that fertility transition starts to approach the rate of replacement where the death rate has also declined. So some examples of countries that are experiencing phase 3 are India, Gabon, Malaysia. So you start to see more approaching of a stability in the population change, and the rate of population growth starts to decrease. In phase 4, countries like Brazil, Germany, Japan, most of Europe, the United States, you see a low to very low birth rate and a very low death rate due to increased healthcare, and this returns us back to a modern stability, which was experienced in phase 1, stability in the population change, so very low population change, and that's where we're basically headed, many countries. So where we used to have relatively stable population in the world, this phase 2 and phase 3 caused that rapid exponential growth in the population, and now we're approaching a phase 4 in many countries where we're coming back to a stability in the world's population. So think about it. Why do you think it's important to be aware about population changes and to incorporate estimates of population growth and population changes in demographics? Why is it important to incorporate that into engineering design? All right, we're going to wrap up this lecture on the topic of sustainability and sustainable development. What does that mean? So before we get into some of the definitions that have been provided by international organizations, I want you to think about, what does it mean to you? Right? So what does sustainability mean to you? You may have studied this in another class, so maybe your definition of sustainability is influenced by what you've learned in other classes, or it might be influenced by what you've experienced in your life or experienced in your interactions. All right, so take 5 minutes, write down a definition of what sustainability means to you. All right, so for the purpose of this exercise, don't worry about consulting a textbook. Don't worry about having a right or wrong answer. I just want to know, what does it mean to you? All right, so now let's talk about how sustainability has been defined by various international organizations. So in general, sustainability is often considered to be at the confluence of people, planet, and prosperity, or in some cases, it's been termed as equity, environment, and the economy. So sustainability is thought of as the conditions under which humans and nature can exist in productive harmony to fulfill social, economic, and environmental requirements of present and future generations. Right, so this is where, if we look at this as like a Venn diagram, sustainability would sit at the middle of these 3 circles. Now, the United Nations Brundtland Commission in 1987 came up with a definition for sustainable development. And this is probably one of the most widely used definitions for sustainable development today. And it's often expressed in terms of the 5 Ps: people, prosperity, peace, partnership, and planet. Right, so this definition, which is very commonly adopted by engineering organizations as well as other human rights and development organizations, says that sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. right? So when we think about the people aspect of sustainable development, we're usually thinking about ending poverty, ending hunger in all forms, and ensuring dignity and equality for people throughout the world. When we talk about prosperity, sometimes we might be referring to economic prosperity or a more general term of prosperity, but ensuring the prosperous and fulfilling lives in harmony with nature. Peace refers to fostering peaceful, just, and inclusive societies. And the partnership aspect, means working together through solid global partnership to implement sustainable development. And the planet aspect refers to protecting our planet's natural resources and climate for future generations. And the United Nations has also come up with sustainable development goals. Right, so before these goals were implemented, we had the Millennium Development Goals, which were established around the turn of the century and were designed with targets for the year 2015. When the year 2015 came around, the United Nations got together and came up with an additional set of goals that extend beyond 2015, going up till 2030 for the most part. And that's the ones that are shown here. These 17 goals are the UN's Sustainable Development Goals, and many of them have a very close connection to the environment and protecting the environment and environmental sustainability. And also engineering interventions that can help address some of these environmental protection needs, such as goal number 2, which is to end hunger, achieve food security, and improve nutrition and promote sustainable agriculture. So for example, some engineering interventions that might be consistent with this goal are increasing the reuse and recovery of resources from waste in order to promote more sustainable agriculture practices, such as the production of fertilizer from waste products rather than from factories. Goal number 3, also ensuring healthy lives, promoting well-being for all at all ages. Another goal that's consistent with environmental protection and finding solutions to environmental problems is goal number 7, ensuring access to affordable, reliable, sustainable, and modern energy for all. So we talk a lot about, in this class, we're going to talk a lot about renewable energy compared with fossil fuels, and what are some of the drawbacks and advantages of different renewable energy sources when it comes to sustainable development. Also goal number 9, build a resilient infrastructure, promote inclusive and sustainable industrialization, and foster innovation. All right, so many of these goals, and also goal 6, clean water and sanitation for all. All right, so many of these goals have a very close connection to designing solutions for environmental problems. And that's what we're going to talk about throughout the course of this semester.